Hey everybody, my name is David Andersson, and I want to talk about multi-channel signal generation and automation. When we talk about phase coherence, we have to define a few things to make sure we're all on the same page. So when we're talking about phase coherence here, we're referring to a condition where two or more of the signals have constant relative phase to each other over time and temperature. This also implies that they're at the same frequency. We can see the sinusoid on the right here. There's a delta phase that holds over time. A phase-aligned ports means that this relative delta phase is then at zero, so that they are perfectly in sync with one another at the input of the DUT. Of course, things like fixtures will add phase shifts between relative ports, and so you need to characterize these with something like an S2P file, which is measured using a VNA. In Keysight's implementation, we have different options for our multi-channel generators, both standard and option PCH. For the standard option, these ports are phase coherent. However, relative changes are incurred upon frequency change. So for example, if you take port 2 and jump it from 10 gigahertz to 20 gigahertz and then come back to 10 gigahertz, the phase delta between port 1 and port 2 will have changed. However, with our option PCH, or phase coherency, then you can ensure that this delta in phase remains fixed over power, frequency, and time changes, so that you can maintain true phase coherence across different test conditions. In today's demo, I'm going to be using a VXG or M9484C vector signal generator to show how to automate some of this. This is a 1 through 4 port vector signal generator. It can also be cascaded with multiple instruments to create even larger multi-port systems. So I wanted to highlight that you can tune the phase of one port relative to another across plus and minus 180 degrees with a phase resolution of 0.001 degrees. And when switching frequencies, we have a phase repeatability of 0.0001 degrees. So very precise. This is all enabled by our DDS signal generation architecture. Why would you want to do something like this? So a couple of common test scenarios that we've observed are things like this, where we have a multi-channel DUT, device under test, with a lot of active channels behind each RF port, so a data converter behind each RF port feeding into a larger DSP engine. And here you want to do a lot of different types of multi-port testing where you control the phase of one port relative to another. In this setup here, you have one reference channel that's being fed by one channel, and then the other channels being fed by the second channel of the signal generator on a mechanical switch. Of course, you could also build a test system where you have a independent vector channel for each of the DET's channels. And the bottom right here, you can also see that VSA, or vector signal analysis software, can be used to load the IQ data collected by the DET directly into the measurement software for visualization and DSP. A similar DUT to what I just showed before is also something like an analog beamformer integrated with converters and a data converter, all in a single chip or a single board, where you don't have any access to any of the analog outputs of the beamformer. So a similar test setup is shown here. In today's setup, I'm going to be using a M9484C VXG vector signal generator paired with a N9042B signal analyzer, the UXA, and I had out of each port of the VXG a different delay path because of different length cables feeding into a power divider at the input of the analyzer. The power divider will here act as a combiner, and this specific one is spec'd up to 50 gigahertz. In today's experiment, I'm going to connect the two channels of my signal generator to this power divider. Channel 1 will be my reference signal, and channel 2 will be my phase shifted signal. So I'll be coming in at the same frequency and sweeping the phase of channel 2 relative to channel 1 and measuring the amplitude on my signal analyzer. What you're going to see is this pattern of constructive and destructive interference. It's shown in the plot on the right here, where the peak will be where the two signals are perfectly aligned in phase at the signal analyzer, so combining and creating a larger amplitude. And then at the trough here, it's going to be perfectly out of phase and canceling each other out. This is very similar to what happens over the air with a phased array antenna, and the two elements are constructively or destructively interfering with one another to create different types of beam patterns in different directions.